We're moving on to look at rate equations and what's known as order of reaction. Now, if you're okay with indices and logarithms, this will be quite straightforward. I don't want to sort of spend too much time on that because I may add quite a lot of confusion. We'll see how it goes. But again, I'm going to work fairly closely from my notes so that I don't deviate away from that too much and do things in the wrong order, because there is always a bit of a risk of that. If I do it without notes, I get distracted and I start talking about something that's coming perhaps next week or the week after or not at all, and we could do without that. So rate equations and orders of reaction. Or I could just say order of reaction. That would do, actually. But different reactions have different orders, which was why I originally said order. Okay, now what you're going to be doing in the assignment for this is carrying out some practicals that will enable you to build your own rate equation for a reaction, because a rate equation only applies to the reaction as it occurred in a particular situation. So rate equations are described as being experimentally determined. You know, there isn't one that you can look up, for example. But what we're looking at is how a rate varies in relation to concentration. So it's how rates are affected by concentration. We will actually be looking at the effect of temperature on rate, but that's further along. That is a separate bit. So at the moment, what we're considering is the effect of concentration on rates of reaction. So it's worth pointing that out, that rate equations are experimentally determined. All right, there's no fixed theoretical rule for them. And the idea of a rate equation is that it shows how rate is affected by concentrations of reactants. So how rate is affected by, and I'll just use the square brackets to say concentration of reactants. All right, now the first bit of this, before it gets actually sort of involved with any numbers, let's just start out. If we've got a reaction, we'll use the same simplified version as we had yesterday. So for a reaction, which is just the A plus B, gives us AB, all right, no other balancing required or anything like that. We've got several important bullet points I'm now going to make, and then we'll start applying the ideas to some numerical examples. And the first thing that we need is the actual rate equation. All right, and what that's doing is relating the rate to the concentration of both reactants A and B. So the experimentally determined rate equals, right, now I'm not sure, have we met any constants before? I don't think we have yet. Lowercase k, very important, lowercase k, and that is the rate constant. Later on in this learning outcome, we do equilibrium. There is also an equilibrium constant, which has the letter k. That is an uppercase K. So no, it's a symbol rather than a unit. All right. So lowercase k is the rate constant multiplied by the concentration of reactant A to the power m. I'll tell you about these in a minute. Also multiplied by the concentration of reactant B to the power n. All right, I'm not going to talk about indices at this point. We'll wait until it all goes horribly wrong. Right. So far, all right, k times a to the m times b to the n. Now, k in this, being the rate constant, that's fine, but to be honest, you'll think by the time we've done this that k is simply a sort of fiddle factor. It's a number that you need to multiply it with to make it work. And yeah, it is sort of. You can't look it up. When we say a constant, you expect it to actually be a number you could look up somewhere, like pi is a constant, isn't it? E is a constant. You know, there are plenty of numbers that have values that are literally constants. But the rate constant, although it's constant for a particular reaction at a given temperature, that's the only constant thing about it. All right? So that's my opinion of chemistry. So what we've got there is, let's identify these bits then. Let's identify K first. So K is the rate constant. Okay, so always the same. So at least it does have that constancy. For a given reaction at a given temperature. There is a relationship between K and temperature. If you raise the temperature, you'll raise K. If you lower the temperature, you'll lower K. So if I just put that in, increased temperature results in increased K. So when you come to the later part of the assignment, for the practical part of it, the first part you're looking at the effect of concentration. So you do different concentrations and measure the rate, and then you take one of those concentrations and you vary the temperature and look at the effect of temperature as well. So they're two separate things here. All right. Now, the M and the N also need to be explained here. Now, M and N are known as the order of reaction, or they are the orders of reaction, because there's two of them. And they are with respect to those particular reactants. So M is the order of reaction with respect to A. N is the order of reaction with respect to B. Now, we don't know what that means yet, but that's where we're going. All right, so I'm just defining the terms to start with. So M and N are orders of reaction with, now unfortunately this doesn't write very well, with respect to A and B respectively. That's not good sentence structure, but that is, in that order is what it means. So M is the order with respect to A, N is the order with respect to B. We can talk about an overall order of reaction. Now, a little bit on indices. If you multiply two indices together, what do you actually do? You add them, yeah. So the overall order of reaction is actually M plus N. All right? So because they're multiplied up there, what that ends up meaning is that the overall order of reaction equals m plus n. That's actually not something we're going to need very much. And then we just need to define the rate thing. That's the other part of the formula that we've got. That rate is, well, change in concentration and this is what we were doing yesterday, really, of, I'm going to put a reaction species rather than saying a reactant, because we could be looking specifically at one ion. And as we get to the assignment, we will do, because you'll use a substance called sodium thiosulfate, and we always refer to it just as thiosulfate, and it's S2O3 2- ions. So it's not actually the whole reactant, it's just part of it. So changing concentration of, and then it's a reaction species. And in this case, you know, this is the chemists stealing a biology word, I think. I don't know, might be the other way around. But it just means a very specific entity, if you like. That a species could be a molecule, an ion, an electron. So it's the change with time, and we're using the units that we worked out yesterday. So we're looking at moles per decimeter cubed per second. All right, so that's our definition, and everything else we do now sort of, hopefully, we'll elaborate on that a bit. So this business about order of reaction. Let's sort of head this a bit so you can see where we're going with it. It might even have been worth starting a new screen for it, but this will do. Obviously, you know, simplest reaction where you've got reactants producing a product, you'd have two reactants. You can have reactions involving more than that, but we're going to stick with two reactants. And if you're investigating the effect of concentration, what you have to do is to take one reactant at a time. You keep one of them constant concentration, and you vary the concentration of the other. And you measure the rate so that you can see what effect varying the concentration of whichever you've chosen has on the rate of reaction. So let's say A and B reacting together to produce AB or C or whatever you want to call it. If you want to know the order of reaction with respect to A, you keep B constant and you do various concentrations of A and measure the rate. And then this is where understanding indices will come in. If you want to know the order of reaction with respect to B, you keep A constant and you vary the concentration of B and measure the rate. In order to get a rate equation, of course, you'd have to do both of those because you need to work out M and N to actually be able to write a rate equation. Right? At the moment, that won't make a lot of sense, but we will get to that point. So let's start. If we've got an equation, let's just stick with the same one. For that reaction, I'm going to write AB. In my notes, I've actually got C there. A plus B gives C, but doesn't really matter. Let's say that for that, it was found, so this is an example really, I should have made that clear. Experimentally, the rate was equal to rate constant, lowercase k, A concentration of A to the power 1, interesting one to think about, multiplied by B to the power 2. How on earth do you find all that out? Oh, once you've got the numbers, you can do it. You wouldn't normally bother putting 1 in as an index, would you? Because anything to the power 1 is, no, itself, yeah? If it's the power 0, it's 1. To the power 1, it's itself, and then power 2, it's squared, and so on. You can actually have fractional orders, and you'll probably find when you work it out practically, oh, it's bound to come out somewhere fractional. You have to do a lot of sort of creative rounding up or down to try and get it to 1 or 2, or just something that's usable. Because in reality, nothing is quite as straightforward as you'd like it to be. Right. How would we know? Well, we've got A and B to consider. Now, the way that we would express this is that we can say that the order is 1, if you like, with respect to A, or it's first order with respect to A. They both mean the same thing, all right? So its order is 1, or it is first order. If, when you keep B constant, if you double the concentration of A, the rate doubles. If you quadruple the concentration of A, the rate quadruples. If you multiply the concentration of A by 1,000,000, the rate is multiplied by 1,000,000. Because what the rate is being multiplied by is the concentration to the power 1, isn't it? And it's that 1 that makes it first order. So you would be able to work that out from practical measurements, wouldn't you? See, if you have a concentration and you could double it, and you can measure the rate, and that doubles as well, well, it's gone up by double to the power 1, right? Fairly straightforward. But I'm going to give you a lot of examples to play with. So I need to write that down so it's obvious. I don't know about obvious, but all right, the order is 1. In other words, we could also say that it's first order with respect, I shall probably just condense with respect to the WRT further on. So with respect to A, all right, not A in square brackets, this is just substance A. All right, so it's with respect to A, if the concentration of B is kept constant, and right, concentration of A times 2, all right, if we doubled it, causes rate to double, essentially. Let's just say, well, let's say to double. In other words, it's times 2 to the power 1. And it's that 1 which is the order of reaction. I'll put some others in. All right, if you took your concentration and multiplied it by 4, then if the effect was that the rate is going to quadruple, right, it's times 4, the same number as you'd got over there, but to the power 1. And then if you wanted to make it general, multiplying it by some sort of factor, which could be any number you like, causes the rate to multiply by factor, I just have to call it factor, to the power 1. So that is a first order reaction. Now, at the moment, we haven't actually got any numbers here, so it's a bit hard to see what's happening, but this will make more sense, I promise. And that would be the experimental part of it. Now, what you'll have two reactants. You can't actually increase their concentration, so you would go down, all right? But, you still have a selection of different concentrations. Now, the other one, if you look back up there, we've got the rate was K multiplied by the concentration of A to the power 1 times the concentration of B to the power 2. So that's telling us that it's second order, or the order is 2 with respect to B. And it's the same sort of process here. We're going to keep the concentration of A constant and then do things to the concentration of B. So the order is 2, or second order. It's a second order reaction with respect to, all right, WRT, with respect to. So don't use it in the assignment, but, in terms of notes, because we say it a lot in this particular unit, it's always, oh, the order with respect to this and the order with respect to that. It's just easier to do. All right, so with respect to B, and then it's I need to just be able to reflect what's up there. If the concentration of A is kept constant and taking B and doubling it, what do you think that would do to the rate if it's second order? Any offers? If you follow through for A, if you multiplied the concentration of A times 2, if it's a first order reaction, then the rate goes up by 2 to the power 1. So if you double the concentration of B and it's a second order reaction, the rate will go up by 2 to the power 2. You've got it. There you go. You've cracked it. That's this afternoon sorted. Yeah. All right. So causes the rate to, I suppose this one is quadruple, isn't it? Yeah. You've got a very, very logical pattern. Once you can see it, to start with it makes little sense, but when you can actually see the numbers. So it's that 2, the little index there, is it's the order of reaction. So you could actually probably fill in the next line. So if you took B and, yeah, so it would be, yeah, there isn't a word for it, but times 4 to the power 2, yeah, it's going to, so yes, the rate is going to go up by 16. Yeah, I'm not sure there is a word for that. Hexadecipli, hexadeciple, that causes rate to, I'm just going to have to put times 16, all right, which is 4 to the power 2. So it's whatever you've done to the concentration, the rate goes up by that to the power of the order. Yeah, we're getting there. So similarly, if you just used the word factor like we had for the first one, just so that I want consistency through this. Should be an S on there. Multiplying it by a factor causes the rate to multiply by that same factor, but to the power 2. So that's where the order fits in. Now, you can have other orders. As I said, you can have fractional orders, but we try and avoid those if we can. So, yeah, some creative graphs and rounding has to take place when you do the practical work. It can go up to 3. All right, we're not going to put all that in as well because it doesn't relate to the one I've got up there. You've got an overall order for this. What's the overall order for this reaction then? Go back to the rate equation up here. The overall order is the two orders added together. So it's 3. Yeah, 1 plus 2. So the overall order of this reaction is 1 plus 2. It's not often I get the chance to write 1 plus 2 equals 3 on the board in an access class, I must say. You can have a 0 order. What would happen to the rate if you increase the concentration? Stays the same, yeah, because anything to the power 0 is 1. So increasing the concentration doesn't affect the rate. Now that's quite an interesting idea, isn't it? Because we would just assume that if you increase the concentration, you increase the number of particles, you increase the likelihood of collisions, but it doesn't always apply. And that is one of the things that we were saying earlier on. Oh, if you increase the concentration, yes, it'll increase the rate of reaction. But that was in our sort of level 2 introduction. What we're now saying is that not always. All right. So you can have a 0 order, and you may well meet one. So 0 order with respect to either reactant. Doesn't matter, but changing concentration, and I'm just going to keep using those square brackets for concentration because it's quicker, has no effect on rate. All right. Right, so that's the first bit then, this idea of orders of reaction. If you had, I'm not sure that this example actually takes us anywhere else, but it's in the notes, so I'm going to write it down anyway. If you've got a reaction, let's use some different letters, that P plus Q gives you R. If the experimentally determined orders are such that with respect to P, so with respect to P, all right, that means keep Q constant but keep changing P. And if we found that the order with respect to P was 2, but if we kept P constant and varied Q with respect to Q, we found that actually varying Q had no effect on the rate of reaction. What would the rate equation be now? This is really just doing it backwards, I suppose. We'd say rate equals... What's the first thing we have to write? K. Then square brackets P to the power 2. And then theoretically, yes, you'd write Q to the power 0. But in fact, we lose that because that Q in square brackets to the power 0, of course, is 1. So actually all we need to write is that for that reaction, the rate equals K times the concentration of P squared, because Q doesn't have any effect on it. All right, you're going to work out your own rate equation for a reaction. Practically, you're going to do the measurements and work it out. Not for a while yet. Now the next issue that we've got is the units for the rate constant, because they vary. All right, this is another thing about how constant it is. There's a huge variety of possible units for it, but they will depend on how many terms there are on the right-hand side. Because obviously, the index that is multiplying your concentrations is very variable. They could both be 1, they could be both 2s, you could have a 0, you could have a 3, there's all sorts. And what we've got to do is to have the units on the right side of the equation, formula, whatever we're going to call it, matching the units on the left, which are always the same, because rate is always moles per decimeter cubed per second. So K, it is a fiddle factor in terms of its units, because we have to use its units to convert all the units that we get out of, in this case, P and Q. We have to get them back to what is on the left-hand side. So this is where it does get a little bit tricky, if it hadn't already. Right, so units for K. All right, the rate constant. They depend on the rate equation. This is where your understanding of indices is actually really important. Now, if we just start with the obvious, the stuff that we know. If we start with this, let's just have a general rate equation, the one that we had earlier on. So for a general rate equation, which is the one that you will usually see, you'll probably see it in those handouts I've just given you, where the rate equals K, then A to the M, B to the N. Sorry, that got a bit squashed. What you've got that you know already is that the units for rate we know. So on the left-hand side, we know that we've got moles per decimeter cubed per second. And we know that the units for concentration, which are on the right-hand side, are moles per decimeter cubed. Now that tells us some feature that we're going to need in K already. One of the components has got to be, seconds to the -1, hasn't it? So all the different units for K will all have seconds to the -1, because you can't get them on the right-hand side any other way. But they're there on the left, so they've got to be on the right. So all the different forms of the units that we're going to get for K are all going to have something times seconds to the -1. However, other than that, it gets quite messy. Right, I'll give you some examples. I think the easiest way, because the way I've got it written in my notes isn't really going to help. I don't know, if I just write, let's see. All right, if I'll stick with that. So, that's a useful word, actually. I've not really encouraged people to use that when you're writing out calculations. All right, you can put, this is this, and this is this, and this is this. So, and that can be your final calculation. You can, you can put that in, because so it's sort of, it shows that logical progression through your work, really. Hopefully, this will be logical. All right, let's see if I can make this work then. If we've got our rate then in moles per decimeter cubed per second, I hope I've not taken up too much space already, it's quite possible, equal K, and then it's the A to the M, B to the N, and then we've got moles per decimeter cubed for each of those, but of course, to what power? M plus N. That's where that comes in useful. However, working out literally moles per decimeter cubed to the power of M plus N is quite messy. All right, but that's what we've got to resolve, if you like, because K has actually got to bring it back to moles per decimeter cubed per second. So let's have a look, see if we can rearrange that. Yeah. Right, if we rearrange what we've got there, so this is requiring your algebra as well. K, therefore, is going to be the rate divided by A to the M, B to the N. If we rearrange that simple version of it, not put the units in yet. So the units are, on the top, we've got moles per decimeter cubed per second, right? And then on the bottom, we've got that bit over there. This does work. And then you get in a bit of a mess here, of course, with negative indices. Because if something's on the bottom of a fraction, of course, that's where you've got, you're multiplying by something to a negative index, aren't you? And what you end up here with, well, let's see if you can you simplify that at all? Anybody? You can cancel something out. You can actually cancel a mole per decimeter cubed. Yeah. What would we be left with on the top? Just seconds to the -1 on the top. But what would we have on the bottom? Moles per decimeter cubed to the power of M plus N. We've got to cancel one. We took it off the top. We've got to take one off the bottom. So it's M plus N -1. We lose one. Yeah? Does that make any sense? Let's. I could write them out, is what I think might help. But moles per decimeter cubed to the M plus N. I suppose that's got to go in brackets really, but it doesn't need to. But we've taken one away because we cancelled it with the top. Is everybody getting that okay? Or see the sun? No, you're not. Okay, that's fine. If, for example, M plus N was 3, what we would have, I'm going to put a line under that and then just illustrate it. So, e.g., if M plus N is 3, then what we've got on the top is we've got our moles per decimeter cubed per second, and on the bottom I'm going to write it all out. Up there it was moles per decimeter cubed to the M plus N, and what we're saying is that is moles per decimeter cubed times moles per decimeter cubed times moles per decimeter cubed. Yeah, that is moles per decimeter cubed to the power M plus N, if that's 3. Is that okay? Are we getting there? Yeah. I love that when you see the little light bulbs go on, and that's the beauty of this job, is when you just come at it from a different angle, and oh right, and you see people's eyes light up a bit, and the nodding starts. So yeah, sometimes you have to do that. You have to expand it out, or sometimes I'll draw things or whatever. So yeah, you can now see that if we were to cancel that with that, what we're left with is seconds to the minus 1 on top, and then moles per decimeter cubed to the power 2 now. So we lost one. It's n plus n minus the one that we cancelled out. So I've now got to complete that, haven't I, really, if it's going to be on here. So we've now got our moles per decimeter cubed to the power 2 instead of the 3 that we had. So that's our 3 minus 1. Good. Right. So that up there, seconds to the minus 1 multiplied by, yeah, that lot down there that's underneath, or divided by that, although ultimately we will bring it to the top, is going to be a little tricky to work out. So let's have some examples. Right, so if we go for, if we've got a rate equation where rate equals, I'm just literally using the ones I've got on the sheet in front of me, k equals a, just to the power 1, sorry, k equals a, sorry, rate equals k times concentration of a to the power 1, units of k. All right, what's n plus n on here? 1. Yeah, we've only got a 1. And then on the bottom, it's n plus n minus 1, so we end up with nothing. Yeah, so the units of k, all we're left with is, yeah, the seconds to the minus 1, the bit off the top. Yeah? And if you look at that then, if I now fill that out, so what we're saying is that the rate where we've got moles per decimeter cubed per second is, well, for k, we've got the seconds to the minus 1 multiplied by moles per decimeter cubed. So, you know, you can see that what k is doing is turning the right-hand unit into the left-hand unit. All right. Okay, let's try. Where's she gone? Let's try another one. Right, let's number these as I go in case I need to refer back. Right, for a second one, if we've got rate equals k, a to the 1, b to the 1, units of k. Now this is where it will start getting a little tricky. If we just use the, so we're going to have to sort of, what's the word I want? Not expand, but sort of simplify in a way. The units of k using the, let's go back up here, whoops, using this, all right, that's really important. If we use that to work this out, n plus n in this case is 2, right. We know we've got seconds to the minus 1 on top. We will always have that. So on the bottom, we've got moles per decimeter cubed to the power 1. We don't need any fractional anything. No, oh, a fractional unit. I see what you mean. No, we wouldn't tend to put it like that. So what we've now got to do is, yeah, we've got to change that, haven't we? So that is seconds to the minus 1, and then how would we write this? I'm going to just, so that's to the minus 1, yeah. All right, now this is messy. if we go through, then what we've actually got there is seconds to the -1. I've got this all in the wrong order for now, but we'll rearrange it when I've finished. We've got moles to the -1, but decimeter cubed to the 3. So what we end up with here is moles to the -1, decimeter 3 per second. And that is not a unit that means anything, is it? It's not something you can do. It's like per moles decimeter cubed per second. It isn't. And this is why I say it's a bit of a fiddle factor, that K, the units of K do vary just to get back to what's on the left-hand side. All right. You could rearrange that. I've just kept them in the same order as we've got in rate because I feel that's the best way to do it. But you could rearrange them so they almost made sense. You could say it was decimeter cubed per second per mole, but that doesn't really because decimeter cubes aren't changing. So I would rather leave it in the same sequence as you've got in the rate. Right, let's try another one. So this is number 3. And needless to say, this one is getting a little more complex. For rate equals K, A to the, what have I got here, 2 and B to the 1. So the units are, well, you know, it's seconds to the -1 on the top. So on the bottom, we've got moles to the decimeter, sorry, moles, oh, I was going to write moles again. Moles per decimeter cubed at the bottom to the power what? 2. Right, let's rearrange that then. See if you can do it without the intermediate stages. Moles to the, yes, so moles to the power of -2. What about the decimeter cubed? To the 6. Yes. All right. Then, all right, so that's where m plus n equals 3. Now you can imagine if m plus n equals 4, if they were both to the power 2, you'd just be doing another multiplication. So it'd be moles to the -3, because it's 4 minus 1. Decimeters 9, because it would be 3 to the 3. Yeah? So there's a pattern here, but they are seriously messy. The one you get in the ones for the assignment, I think, are not complex, but you do have to get them right. They are some of the simpler ones, all right? But I need you to just sort of see where this is coming from. So these units for K are a bit on the ridiculous side because they are literally there just to sort of balance the two sides in terms of their units. Right, I'm going to give you an example to have a look at now. So I'll put this on pause. Okay, let's have a look at what we've got then. Because just looking at this sheet, you look at it and you think, I haven't got a clue what this means. We've got a reaction then where A and B are reacting to form products. Good, okay, I think we can understand that much. One thing I should probably add here is that, yeah, it is good practice to put the state symbols after the reactants, and you can see in the results table there, when you're talking about the concentration of, then state symbols, aqueous, you know, if it's in solution, is a sensible thing to put. But you have to be realistic sometimes in terms of the amount of space you've got. What we have there are 3 experiments, if you like, 3 reactions being carried out. Where one of the reactants is having its concentration changed between a pair of experiments while the other's kept constant, and then the other way around. I don't know if you can see that. If you compare experiment 1 and 2, what's being kept constant? B. What's happening to A? It's doubling, isn't it? And is the rate changing? Yes. So that, that will give us a way of looking at the order with respect to A. And then between, well, which other two can you compare? You could compare 1 and 3 because what's being kept constant? A, whereas B is being doubled. And does the rate change? It does. Okay, so that's the information that you get off these sheets, and that wouldn't have necessarily jumped out at you straight away. So we've got two things to do. I've sort of ignored the question here, but the first two parts of it, use the data from figure 1 to deduce the order of reaction with respect to A. We don't need to explain it necessarily. As long as you've done it, you'll know how you did it. And for part 2, deduce the reaction with order of reaction with respect to B. Now, if we do that one at a time then, with respect to A, it means keeping B constant. So I'll do that one, is going to be in red. And what we have, I find it helps sometimes to draw all over these, what we've got there is a times 2, while that's constant. All right, so const, I think, is all I can fit in there. What happens to the rate from here to here? The rate has gone from 1.64 times 10 to the minus 6 to 3.28 times 10 to the minus 6. What's happened to the rate? It's doubled. So it's gone up by 2 to the power 1, yes. All right, so the order with respect to A is, we've kept B constant, we've doubled A, and the rate has doubled. It's gone up by 2 to the power 1. So the order with respect to A is, it is the 1. All right, it's that power, isn't it? The M. All right, so the order is 1. It's that 1. Now, I don't think the other one gives us any greater challenge, actually, does it? With respect to B, which I'll do in blue on here, then if we are keeping A constant, then we must be using those two. I've got a whole sheet of these that you're going to have a go at. So we've got the constant there, but for that same reaction, here to here has gone, well, what's the increase there? That's times 2, so we've doubled that. So we've got to compare the rate, and what do you know? Same again, isn't it? Yeah? So again, the rate is times 2 to the power 1. So the order with respect to B is 1. Yeah. All right. Now, a rate equation then for the reaction between A and B. And it is literally just rate equals, what's the first thing we write? K. And then it's concentration of A to the power, so we don't write it, times concentration of B to the power, so we don't write it. And so there's your rate equation. And then part 4, a little bit more challenging perhaps. Use the data from figure 1 to calculate the value of the rate constant. Well, we could use any of the experiments to do it. It doesn't matter. You've got a set of data. Well, you've got 3 sets of data. They should all produce the same answer. You feed 1 or 2 or 3 into that equation that we've just done there. So if we were to take, let's just take the first row because it's, the first row really, that any of them would do, all right. The rate in the first row is 1.64, that's it, times 10 to the minus 6. I haven't got room to write this out properly, have I? Equals K times, I'll have to do it on the next, just underneath, concentration of A times concentration of B, and those are literally what we've got in those two squares. So we've got 2 times 10 to the minus 3 times 3.35 times 10 to the minus 3. So that last bit is actually really easy to work out, isn't it? What's 2 times 10 to the minus 3 times 3.35 times 10 to the minus 3 without using a calculator? It certainly is. Well done. 6.7 times 10 to the minus 6. So I'll just keep working down here and trying to line it up a bit. So 1.64 times 10 to the minus 6 equals 6.7 times 10 to the minus 6. And I missed the k out, so I'll stick that on the end. Right, if we want to get k on its own then, we'll divide both sides by 6.7, yeah? Times 10 to the minus 6. So k equals 1.64 times 10 to the minus 6 divided by 6.7 times 10 to the minus 6. Oh, guess what? We can cancel something out there. Let's get a shot of them. And so k equals, yeah, roughly, about 0.25 in my brain. That looks, 6.7 looks like about 4 times 1.6. There we go. All right, 0.24. Is that enough on its own? Oh no, it isn't. We need some units. Okay, what units do we want for this then? What's the overall order? No, the overall is 1 plus 1, isn't it? 2. So, yeah, that minus 1. So that's going to be, that's our moles to the minus 1 decimeter cubed second to the minus 1. If you look back, yeah? Moles to the minus 1 decimeter cubed second to the minus 1. I think, where we've got, if I remember rightly. Yeah? So, yeah? Yeah? Is that okay? All right. God, I've done a lot this afternoon so far. Still a bit left. Just examples, really, just to set that in your mind now. And that's why I'm not progressing with anything else, because you know people who've missed this are not going to find it easy. So let that be a warning on the recording. Right now. This is a sheet which is it's got stretch and challenge on it, but we're not being observed, so it doesn't really matter. On the first side, you've got 4 examples that are rather like the one we've just looked at. They're not laid out exactly the same. I suspect. I don't know if I've gone out of range of the receiver. But on the first side, you've got 4 examples that are laid out a bit like that one. They're not quite the same. It just tells you what. Well, I don't know. Yeah, you have got actually 3 columns the same, haven't you? And over the back, if you want the stretch and challenge, it's actually a different reaction involving 3 reactants rather than 2. But needless to say, of course, if you've got 3 reactants, then the rate will be K times A to its power, B to its power, times C to its power. So, you know, it's following the same principles. All right. So I'm going to stop the recording at this point, I think, because I do actually have an answer sheet for these somewhere. So I'll try and find that. But I would suggest work together on some of these. All right. But we want to get these fairly secure, I think, at this point.